Today we're going to talk about the Tacoma Narrows Bridge. Before we do so, let's review some ideas from before about amplitude and the phase of the steady state. Recall that we're considering a second order differential equation, y double prime plus p times y prime plus q times y equals g of t, where we have sinusoidal forcing. That is, g of t is equal to a constant, capital K, times cosine omega t minus theta. Here, capital K is the amplitude, omega is the angular frequency, and theta is the phase angle. We'll assume that the damping P is not too large. That is, P squared is less than 4Q. If this is the case, then we know the general solution by looking at the roots of the characteristic polynomial, namely alpha plus or minus beta I. The extended linearity principle asserts that the general solution is y of t equals a constant k sub 1 times e to the alpha t cosine beta t plus a constant k sub 2 times e to the alpha t sine beta t plus a particular solution y sub p of t. In order to describe the particular solution, we need to consider two cases. First, let's say that q minus omega squared plus p omega squared does not equal to 0. Then there is a periodic solution of the form y sub p equals capital A cosine omega t minus phi. We can express capital A and phi in terms of the expressions you see on your screen. In the second case, when q minus omega squared plus p omega squared is equal to 0, then there is a solution of the form y sub p of t equals capital A times t times sine of beta t minus theta. Notice that as long as p is positive, all solutions y of t are approximately equal to y sub p of t as time t increases without bound. Assuming, just like before, that p squared is less than 4q, the assumption p is equal to 0 is unrealistic because there is always some damping, so we may as well assume that p is positive. Recall that if the forcing term g of t is sinusoidal, that is equal to capital K times cosine omega t minus theta, then our response y of t is approximately equal to capital A cosine omega t minus phi, where capital A we can express as capital K divided by the square root of q minus omega squared plus p omega squared. And our phase angle, capital Phi, is equal to theta plus the arctangent of p omega divided by q minus omega squared. Notice that both the amplitude capital A and the phase angle phi are functions of the frequency omega. We're motivated by the following question. What is the largest amplitude capital A we can find, and at what frequency omega does this occur? We found answers to both of these questions in the following proposition. As before, let's assume that the roots of the characteristic polynomial are complex numbers. That is, lambda equals alpha plus or minus beta times I. Moreover, let's assume that we have sinusoidal forcing. That is, g of t equals capital K times cosine omega t minus theta. First, we see that the maximum value of the amplitude capital A is equal to k divided by twice alpha beta if alpha is less than beta, or it's k divided by alpha squared plus beta squared if alpha is greater than beta. Second, this maximum value for the amplitude occurs at either omega equals the square root of beta squared minus alpha squared if alpha is less than beta, and omega equals 0 otherwise. In particular, there is a non-trivial resonant frequency omega if and only if alpha is less than beta. Finally, at this maximum value for the amplitude capital A, we have the following phase angle. Either phi is equal to theta plus the arctangent of omega over alpha, where omega is the square root of beta squared minus alpha squared, or phi is equal to theta when omega equals 0. Today, we're going to talk about a situation that happened back in Washington State in 1940. We're going to discuss what's called the Tacoma Narrows Bridge. I highly recommend that you watch this short 3-minute documentary on YouTube that gives a bit more detail of what happens, and also it has some video footage of what happened back in 1940. But today, let's try to discuss what happens here mathematically. In 1937, the Washington state legislature decided to build a suspension bridge to connect the city of Tacoma to Kitsap Peninsula over the Tacoma Narrows Strait. This would be the longest bridge, the third longest suspension bridge in the world. The plan for this bridge would make it at 2,800 feet. By comparison, San Francisco's Golden Gate Bridge, which was built in 1937, has a span of 4,200 feet, and Manhattan's George Washington Bridge, which was built in 1931, has a span of 3,500 feet. Construction on the Tacoma Narrows Bridge began on November 23, 1938, and it was finished in early 1940, about a year and a half later. Even before the bridge was open to the public, workers noticed that in light winds, the bridge deck developed a rippling vertical wave phenomenon. Because of this, they nicknamed the bridge Galloping Gertie. Still, the Tacoma Narrows Bridge was opened to traffic on July 1, 1940. Some 10,000 individuals turned out for the dedication and opening of the bridge. But even then, the rippling motion continued. Bridge engineers worked to find a solution to dampen this movement. But when these methods failed, they hired civil engineering professor Bert Farquharson from the University of Washington. He helped design the bridge, and they felt that he could help to solve the problem. However, on November 7, 1940, the bridge began to behave differently. Instead of its typical galloping motion, it turned to have a violent twisting motion. And at 11 a.m. that day, the bridge collapsed. Here's a quote from Bert Farquharson as he was on the Tacoma Narrows Bridge that morning when it collapsed. I was the only person on the Narrows Bridge when it collapsed. I didn't believe it would happen, and besides, I was anxious to get a motion picture of the unusual way the bridge was acting for my official records. When I arrived at 9:45 a.m., the bridge was moving in a normal way, in the familiar rippling motion we were studying and seeking to correct. About half an hour later, it started a lateral twisting motion in addition to its vertical waves. It had never done that before. Looking toward the Gig Harbor end, I saw the suspenders, that is, the vertical steel cables, snap off, and the whole section of the bridge caved in. The only fatality that day, fortunately, was a Cocker Spaniel named Tubby. Here's a link to another YouTube video that actually is a newsreel by the British Pathé that explains a little bit more behind what happened that day. Simply put, engineers were very curious to know what made the bridge collapse. What they immediately realized is that the twisting motion of the bridge probably was caused by what's called aeroelastic flutter. If you look at the diagram here on the screen, as the wind moves from left to right, you can see that there are certain vertices that are kind of peeled off based on the cross section of the bridge. If the vortices are very strong, they can actually cause this twisting motion. In a sense, this is like a wing that's kind of twisting and flapping in the wind. In fact, engineers even thought that there were a couple of simple fixes in order to make sure that this bridge would never collapse again. Again, remember that they thought this aeroelastic flutter was what caused the collapse. So they figured, number one, they could probably drill holes in the side of the bridge so that that way air would flow through and you wouldn't have these vortices that would form. Another suggestion was to have curved outriggers on the side of the bridge. That way they divert the wind to go around and they wouldn't cause the vortices. But today we're going to have a different question. We'd like to know, can we explain mathematically why the bridge collapsed? Well, let's recall what behaved differently about the bridge when it did collapse. For the first 4 months the bridge was in use, that is, from July through October of 1940, the bridge underwent undulation. That is, there were simply ripples that moved along the length of the bridge. However, in November 1940, something different happened. The bridge started to twist from side to side. This means that we're going to try to keep track of two different variables here. First, we'll keep track of the height y along the center of the bridge. And second, we'll keep track of the twisting angle theta. You can see at the lower right-hand part of your screen, you have a cross section of the bridge. On both sides, you have these suspenders These will be the long vertical cables. And towards the bottom, here you have the actual road side of the bridge. You'll notice that this road side can now twist according to some angle theta. But also, the concrete part of the bridge can move up and down. This will be the vertical deflection of the center of gravity, what we're calling y of t. In the 1990s, a mathematician by the name of McKenna was interested in studying the mathematics of such a situation. He said, assuming that the height y and the twisting angle theta are both small, then both y and theta are solutions to an uncoupled system of second order linear equations. We'd like to discuss why in today's lesson. First, let's denote L as half of the width of the bridge. In reality, 2L was around 40 feet. We'll also denote M as the mass at a cross section of the bridge. We're going to view these suspenders, remember that these are the vertical steel cables, as springs. So now we'd like to figure out what can we say about the bridge itself. We'll assume that we have four forces. First, we have the force of gravity, which pulls downward on this cross section of the bridge. That is, there's a force pulling down on the bridge, but we don't have any twisting torque from side to side. So we'll say that F sub g is minus mg, and tau sub g, our torque, equals 0. Second, we have dampings due to air resistance. That is, there's a damping force which acts to slow down the undulation. Remember, this is the up and down motion of the bridge. And it acts to slow the torque. That is, the torque acts to slow down the twisting motion of the bridge. So we'll assume that our force due to damping, F sub d, is proportional to the velocity, so negative b times dy dt. And the torque here for the bridge is also proportional, but this time to the angular velocity. So our torque, tau sub d, is equal to negative beta times L times d theta dt. Third, we'll assume that there are external pressures on the bridge due to wind. That is, the wind will affect the undulation, this is the up and down force, as an external force, and will affect the twisting, remember this is the side to side, as an external torque. So we'll write F sub E, our external force, as F of time, and tau sub E, our external torque, as tau of time. And finally, we want to consider the suspenders, which do act as springs. They have a restoring force that's proportional to either y plus L sine theta or y minus L sine theta. But let's be a little bit careful. The suspenders here only work when we have a stretching of the vertical steel cables. They don't work this way when we have a compression of the vertical steel cables. So this means by looking at the steel cables on the left and the steel cables on the right, we can write the restoring force, F sub s, as negative k times r of y plus L sine theta minus k times r of y minus L sine theta. And the restoring torque, tau sub s, will be proportional to the actual length by which the concrete road is twisting. So in this case, it's negative k times r, evaluated at y plus L sine theta, times the length, L cosine theta, plus k times r, evaluated at y minus L sine theta, times the length, L cosine theta. Notice that all of this is in terms of this function, r of u, which is the minimum of u and 0. In other words, r of u is equal to u when u is negative, but r of u is equal to 0 when u is positive. Now, these last two cases, in terms of the restoring force for the suspension cables, is a little bit complicated. So here's where we'll make our assumption that both the height y and the angle theta are small. If this is the case, then the force due to restoring is approximately negative 2 times 2k times y, and the restoring torque is approximately equal to negative 2 times k times L times theta. Using Newton's laws of motion, we find that the height y satisfies the second order differential equation. Essentially, mass times acceleration will be the force due to gravity, plus the force due to damping, plus the restoring force of the spring, plus the external force. Putting all of this together, We then find that dy dt is equal to v, and dv dt is approximately equal to negative q times y minus p times v minus a function g of t. This here is very similar to some properties of expressions that we've worked out towards the beginning of this course. There's a similar statement now about the torques. After one defines the concept of moment of inertia and shows that the inertia for our concrete slab is 1/3 ml squared, one finds that the angle theta satisfies a similar expression to F equals ma. In this case, the inertia times the angular acceleration is the sum of the torque due to gravity, the torque due to damping, the torque coming from the restoring force of the suspension cables, and the external torque. Putting all of this together, we then find that theta double prime plus a constant capital P times theta prime plus a constant Q times theta is approximately equal to our function g of t. But this is exactly what we mentioned earlier in the lesson today. Let's end by discussing a few examples and trying to decide how does this relate to the actual situation of the Tacoma Narrows Bridge from 1940. First, let's consider the situation where there is no torsion of motion. That is, we're going to assume that there is a light wind which makes the bridge gallop but not twist. We can say this is saying that perhaps we have a force that will act in terms of the horizontal motion, that is g of t equals negative g plus lambda sine mu t. The negative g, of course, is coming from gravity, and the capital G of t will be 0. That is, we have no forcing for the angular direction. There is no twisting. Putting this together, we can then solve the two equations that we mentioned earlier. Y of t equals negative g over q plus some amplitude a times sine mu t minus v, and theta of t is equal to 0. Notice that y of t is now a periodic function which oscillates around negative g over q. This is what happens when we have our bridge, and it will settle a little bit based on gravity. Notice that theta of t is a constant. That is, we have no twisting. This is exactly the situation that we saw with galloping dirty in the first place. Now let's assume that we have torsional motion. That is, let's say that there is a faster wind which does not make the bridge gallop, but which does cause twisting. We're going to say here that our capital G of t is lambda sine mu t, while our lowercase g of t is just equal to negative g. It's just the external force coming from gravity. In this case, we'll find that y of t is equal to negative g over q, whereas theta of t is equal to capital A sine of mu t minus capital V. This is the phenomenon that we discussed earlier called aeroelastic flutter. Here, you can see that the angle theta of t is now periodic and twists back and forth, whereas the entire bridge itself simply sags at some height negative g over q. As a final remark, notice that these are just approximations, assuming that the height y and the twisting angle theta are small. The actual equations to model the motion of the Tacoma Narrows Bridge are much more complicated and are nonlinear. You can see them here on your screen. Recall that capital R evaluated at u is the function that either takes on u if u is negative or takes on 0 if u is positive. Unfortunately, the only way one can solve this system of differential equations is by using numerical methods. Thanks very much for watching.